Alright, so this video here is going to take us through the problems on the final exam that relate to Chapter 7 out of the textbook. Alright, so the first one we'll see on the final exam relating to Chapter 7 is one kind of like this. Look at our objective here. Find the nth roots of nth powers. Alright. Let's just look at our directions that ask us to simplify, right? And then assume the radicand represents a real number. All right. So to basically approach this one, we need to remember the very basic definition of a radical expression. So basically what we have here is the nth root of a. Okay. Basically what this says is that this representation is a number whose nth power results in a being the radicand, right? N being the index of this thing, this symbol being the radical symbol, and the whole thing referred to as a radical expression. Right? So going back to what we said before, this is actually, we could write this as the nth root of a is b, right? And what we were saying there in that case is b to the n equals a. All right, let's reiterate what we just said. We said that this representation here is a number whose nth power is the radicand a. Right? So basically what we're saying here is so the b is that number, and notice that the b is taken to the nth power, and we're getting the radicand a. Okay. So in other words, we're asking ourselves what number here, when we see something like this, can be multiplied by itself this many times to get the radicand a. All right, so to kind of understand how to do this, let's rewrite this one here. We're taking the cube root of x to the 9th. And by the way, we could factor x to the 9th in such a way, rewriting it like this right here, x to the 3rd times x to the 3rd times x to the 3rd. Right? Thinking about the product rule of multiplication, we keep our base x and we add our exponents. So keep the base x, we get 3 plus 3 plus 3, which is 9. Okay. So I hope that you're starting to see where I'm kind of going with this one here. Notice we have the number multiplied by itself this many times. And that is that number. So what we would have here, our result would be x to the 3rd. All right, so another way to think about this that'll further reinforce this concept is to take this particular rational expression here and convert it into a form that uses rational exponents. So that would be x to the 9th to the power of 1/3. Right, so what we're drawing on here is, again, this whole nth root of some number a. And remember, when we talked about rational exponents, we said that the nth root of a is the same thing as a to the power of 1 over n. Okay. Notice that we kept the base a here, and we gave it an exponent. And notice that in that exponent, the denominator is the index of the radical expression. Right, so the reason why I like to do this is because if we were to perform this operation here, and remember, we have a power to a power situation. We have a power to a power. What we do is multiply our two exponents. So actually what we're going to have here is x to the 9/3. Or in other words, x to the 9 divided by 3, and 9 divided by 3 is 3. Alright, so that brings us to another way to think about this here. When we had a situation similar to this, notice that actually what we did there was divide the exponent of the variable here, that is underneath the radical sign, by the index. So again, we get x to the 3rd. I just kind of like to show you these differing ways to think about this, because this is really not a complicated problem. But sometimes students get a little overwhelmed with these things. But if you think of it in these three different ways, it should make a lot more sense. Right, so the next one that you're going to come across on the final exam relating to Chapter 7 will be one kind of like this one here. Look at our objective here. Use the product rule for radicals to multiply the radical expressions. Okay. Notice it says multiply if possible using the product rule. And in addition, if we were to scroll down a little bit, we would see that it says simplify your answer, type an exact answer using radicals as needed. So we have to simplify this thing on the very end. So don't leave your answer in a unsimplified form. Okay. So let's talk about the product rule here. Do you remember that our product rule was written this way right here? Basically the nth root of A times the nth root of B, multiplying there. And that result is the nth root of A times B. Notice we put our two radicands underneath the same radical there. So in other words, what we're saying here is the product of two nth roots is the nth root of the product of the radicals. Also notice that it's very essential that the indexes be the same. If the indexes of these two radical expressions were not the same, we would not be able to apply the product rule for radicals. All right. So let's look at our example here. Square root of 11 times square root of 11. So what we would do here, and I'm going to break it down into a very rudimentary form here, would be the square root of 11 times 11. I'm multiplying the radicands, right? And that is actually the square root of 121. All right. And remember, we want to simplify it at the very end. So square root of 121 is not in its most simple version. Actually, the square root of 121 is 11. So there we go. While we're talking about it, let's think of this particular situation here in a different format. Square root of 11 times square root of 11 is actually the square root of 11 squared. So I like to use the terminology here that we're unsquare rooting it. So if we were to unsquare root 11, we would get 11. Let's use our knowledge here about what we talked about radical expressions written using rational exponents. So we already said square root of 11 is the same thing as square root of 11 quantity squared. So if we were to write that thing using rational exponents here. So what we would get here would be 11 to the 2 over 2 power, and 2 divided by 2 is 1, so what we have there is 11. And yet another way to think about this one is a square root of a number times the square root of that same number is that number. Just a couple of ways to look at this one when dealing with the product rule for radical. All right, so the next one that we're going to come across on the final exam is going to look like this. Notice again, in the objective it says to use the product rule for radicals here, okay? And also, if we were to scroll down, notice it says to simplify the answer and type an exact answer using radicals as necessary, right? So, you may look at this. You may look at this one and you're like, what should I do to this one? But actually, we are multiplying here, indicated by the dot there. And what we are trying to do is get a simplified version of that product. Again, drawing upon our product rule here, right? Basically, keep the index and multiply the radicand. So we can very easily rewrite this one here into a simplified form, so it would be square root of 11n, okay? And just to be sure, that is an n there, okay? So that's all you got to do on that particular one there, is simplify it using the product rule. All right, so when we come to this next one here, the best place to start is to once again look at our objective. It says to simplify radical expressions involving addition and subtraction. There's a lot of things going on in this particular problem. One, remember, we need to simplify the expression, and we'll go into that here in a moment. And then we also need to perform some addition and subtraction on this thing. But probably the best place to start is to look at how our answer should be represented. One, it should be simplified. And then two, we must type an exact answer using radicals as needed. Okay. So sometimes when I've seen students come across this one, they will just type this operation into their calculator, and then they write in whatever the calculator spits out. Let's go to our calculator and look at this operation, this calculation here. Notice that I typed it in as it was, and notice what it returned there. It returned a decimal approximation of this. That's not what we're going for. As it said in the instructions, it wants us to type an exact answer, not some sort of decimal approximation of this thing. Okay, what's going to come next will be the simplifying radical expressions piece. And probably the best way to go about this before we start working this would be to review some concepts on simplifying radical expressions. And we'll draw upon the lecture notes on this one. All right, so if you remember in the lecture notes, we talked about the conditions for simplifying a radical. And there were 4 conditions. And the one that we're really looking for in this particular problem is this one here. The radicand has no factor raised to a power greater than or equal to the index. And then there were these other requirements that we also discussed. But we want to focus on the first one here for this particular example. So going back of what we said in class, we talked about how the square root of 28 is not simplified. Okay? We don't consider that to be simplified because it violates that first rule there. The radicand has no factor raised to a power greater than or equal to the index. If we were to factor the radicand 28, we could get 4 times 7, right? 4 times 7 is 28. All right. Notice that 4 can be represented as 2 squared. What we have here is a factor raised to a power equal to the index. Remember, our index here is 2. So we have a factor raised to a power equal to the index. That violates that rule. So square root of 28 can be simplified to 2 square roots of 7. All right, so let's think about it this way. That one right there, the square root of 28 equals the square root of 4 times 7, can be written this way here as the square root of 4 times the square root of 7. So what we've kind of done there is unproduct ruled that particular radical expression there. Kind of the reverse of what we've seen with the product rule so far. All right. So 4, the square root of 4 is 2. So we got 2 times the square root of 7, which is our simplified version of this radical. All right, so let's just go ahead and proceed with our next steps on this particular one here. So we'll just bring down the negative 3 square roots of 2 here. And what we're going to do is factor that 50. And we're going to factor it in such a way that what we're looking for is a square root factor. So like 1 and 50 and 5 and 10 are also factors of 50. But what we're looking for is a perfect square factor. So let's go ahead and write it that way, because 25 times 2 is 50, right? 25 times 2. All right. So what we have there is a factor raised to the power equal to the index. 5 squared has a power of 2, and our index is 2. So we'll just continue on with our next line in this situation. And I'm going to include an extra step here just to emphasize the point here. And what we have there is 3 times square root of 25 times square root of 2. I product ruled that situation right there, right? So that brings us to our next line here. Negative 3 square roots of 2 plus 3 times 5. I took the square root of 25, which was 5. Okay. All right. So remember when I take that out, basically, I've got to simplify this product here, 3 times 5. So I've got 3 square roots of 2 plus 3 times 5, which is 15. So now I've got it in this form right here. Negative 3 square roots of 2 plus 15 square roots of 2. All right, so our simplifying the radical stuff we've kind of covered. Now what we've got to do is cover the rules on adding and subtracting radical expressions. All right, so so this was the objective. I believe we were drawing on 7.4. But anyway, notice it says simplifying radical expressions involving addition and subtraction. So here we have a particular radical expression here. Then we have another one right here. What we emphasized was that we can kind of use the distributive property here to demonstrate how we combine these radical expressions of this type. So we got 4 square root of 2 plus 3 square root of 2. So what we would kind of do here would be factor out the square root of 2. So we'd be left with the binomial here, 4 plus 3 times square root of 2, and we get 7 square roots of 2. In a similar way, in this one down here, we did the same thing, only we were subtracting here. we took the square root of 3 out, and then we were left with these numbers on the outside of 2 minus 5. Okay, and then we get negative 3 square root of 3. All right, notice what it says here. This is similar to adding 4x plus 3x is 7x. I think we can all agree with that. So what we're really doing here is combining like terms. And this lower one was similar to 2x minus 5x is negative 3x. So remember when we were combining like terms, what we did was add or subtract the coefficients of x in this example. So in a lot of ways, you can consider these situations right here, and you can consider this number on the outside of the radical. It's kind of like a coefficient of x. All right. But it's very important. Notice the caution here. Only radical expressions with the same index and the same radicand may be combined in this way. All right, so let's look at what we have here. We got negative 3 square root of 2 plus 15 square root of 2. Notice that we have radical expressions that have the same index and the same radicand, square root of 2. Right? So we can combine them in the way we just described. So what we would have there, and let's just go ahead and write in an extra step here. Negative 3 plus 15 square root of 2, which is 12 square roots of 2. Okay. This particular step, you may you could do it mentally. I just included it there to emphasize the concept that we were going for there. All right. All right, so the last one on the final exam is actually pretty simple to do. But when you come across it, you may wonder what it's asking you to do. Well, let's just break it down by our objective here. It says rationalize denominators with one radical term. All right, look at our instruction. It says to rationalize the denominator. All right, so probably the best place to start on this one is just to go down here and look at the conditions and how they want us to enter the answer. Simplify our answer. Type an exact answer using radicals to represent any numbers in the expression. So that's where we should start. Let's go to our calculator here, because a lot of times when I grade these tests, students sometimes will type in the radical expression there into the calculator, and then they will get that decimal there, and then they will write out that decimal approximation. That is a decimal approximation, by the way. And that is not what they're asking for. They're asking for an exact answer using radicals as needed. Okay, so let's back up a little bit, and then probably the next thing we should talk about is going back into our lecture notes on this. And so we pointed out those four rules, but the one that we're looking at here is number 3, that no denominator can contain a radical. No denominator can contain a radical. It's just the way that they want us to simplify these things based upon certain rules. Okay. So what we used there in class was this example here, 7 over square root of 7. It violates that number 3 rule there, that no denominator can contain a radical. All right, and then we said that we could simplify that by multiplying by a form of 1. So what we did was multiply the numerator and the denominator by a form of 1. Square root of 7 over square root of 7 is 1. And what we ended up with there was using the product rule. We get 7 square root of 7 over 7. The 7s would cancel out, and that would simplify to square root of 7. So basically what we did was rationalize the denominator, because what we have there is square root of 7 over 1. Our denominator is now 1. And also similarly, we had a 7. By taking square root of 7 times square root of 7, we got 7. And what we got there was a rational number in our denominator there. All right, so let's just go back. Notice it's asking us to rationalize the denominator. And as I said, what we did there was multiply by a form of 1. But you may wonder, what is a rational number? Let's go back on that particular concept. All right, so the definition of a rational number is a number that can be represented by writing it as a fraction. That is, we could put an integer in both the numerator and denominator to write it as a fraction. Another way to think of a rational number is that it is going to either, in a decimal form, it's going to terminate or it's going to repeat. So conversely, an irrational number would not be able to be represented as a fraction, and in its decimal form, it's not going to terminate or repeat. Let's look at this concept here. All right, so let's go to our calculator again. All right, so what I did was type in a couple of rational numbers represented as a quotient between the numerator and denominator. So 1/3. 1/3 can be represented as a fraction. And then when we calculate it, we get our decimal approximation here. And notice that we have 0.3 repeating. Okay, so that's an example of how a rational number will repeat in its decimal form. And another common one is 1/4. When we calculate that, we'll get 0.25. This is an example of how a rational number will terminate. Okay. Let's consider one of the most popular irrational numbers ever, which would be pi. All right, when we calculate it using our calculator, we get this decimal approximation. Notice it's not repeating. But you might say, hey, it's terminating at that 4. Actually, what's happening is the calculator this particular calculator I'm using only has a float level of 9 digits to the right of the decimal point. So really what it's doing here is rounding off to that 9th decimal point there. Okay, so this is not an exact representation of pi. And as I said, in math, what we like to do is write exact answers instead of decimal approximations. All right, so now let's look at this other common irrational number, which is the square root of 2. Again, we have a decimal approximation, okay? And again, it's not repeating, and it's not terminating here at this 9th decimal place. What the calculator is doing is just rounding to that place. So pi is an exact answer of this decimal approximation, and square root of 2 is an exact answer of this decimal approximation. So whenever your question asks you to write things in exact answer, this is what we're going for. All right, so we're back to where we started here. This question is really not hard to answer, but there is a lot of background on it that can be a little bit complicated. So I did want to kind of go back over that, just so but the big thing is that, answering the question, what does it mean by rationalizing the denominator? And also this additional concept here where it wants us to write in an exact answer. Okay? So that has a lot of background to it. And I hope we kind of addressed that. So what we want to do to rationalize this denominator is multiply this radical expression here by a form of 1. And that form of 1 would be square root of 5 over square root of 5. So you may ask, well, how do I know what form of 1 am I going to multiply for? Well, it's evident right here in your denominator. Notice in the denominator it has square root of 5. So that is the number that I will multiply both the numerator by and the denominator by. Okay. And again, multiplying by a form of 1, we're not changing the value of this rational number here. We're just changing its form. It's actually just going to be the same number, just in a slightly different form. A form that is consistent with our rules on simplifying radical expressions. So let's go ahead and multiply out using the product rule. So square root of 3 times square root of 3 is square root of 15. And square root of 5 times square root of 5 is 5. Going back to that concept before that we said, when you multiply the square root of a number times the square root of that same number, it is that number. We unsquare rooted 5 there. And 5 is a rational number because we can write it as a fraction, 5 over 1, right? And 5 terminates as a decimal representation. As I said, this particular question is really easy. The only questions that often arise are, what in the world is it asking me to do? And this is really all it's asking us to do here. All right, so those are the questions from Chapter 7 that'll be on the final exam. All right, so if you've made it through this far, good job, and also good luck on the upcoming final exam. Drawing a little bit on the famous journalist Edward R. Murrow and something that he used to say in a similar fashion at the end of his broadcast.